So as we move on here, we're going to continue to look at the variance in some more depth. How else can we work around the variance? In the previous section, we looked at how we can find the confidence interval, and we completed hypothesis tests based on the variance. Well, it might seem natural that we're then going to try and compare the variance from two different distributions with each other to see whether they're the same or to see whether there's any differences between them. Okay, so if we were to define each distribution, we can make sure that we use some subtext to identify which one's which. So obviously X's will be for this black distribution, whereas Y's will be red. So I've color coded it so it's a little bit easier to track what's going on. We already knew that n minus 1 times s squared over sigma squared followed a chi-squared distribution. Well, it then follows that one instance of that divided by another instance will also follow a chi-squared distribution, which looks like this in this case. We could also eliminate the n-1 term in each of these cases by dividing. And now on the left-hand side, we've got an expression, a nested fraction, that is the sample variance over the population variance for both distributions. And if you can see, we do kind of have the ratio of one to the other. Now, we've done a lot of fraction manipulation here. It would be fair to assume or to state that the reciprocal of what we have here is also true. Okay, we're going to make an assumption here, a default assumption, that sigma squared for x equals sigma squared for y. If that's true, then actually they can be cancelled out from this nested fraction, and we'll be left with s squared x over s squared y follows this specific distribution. Okay, we've done a lot of manipulation there, and it's really to get to this point where we have this distribution which has two parameters. The two parameters are nx minus 1 and ny minus 1. And this is a very interesting distribution in statistics. This is what we call the F distribution. Okay, so the F distribution has these two parameters. It's basically the n value for one distribution, subtract 1, and the n value for a second distribution, subtract 1. But we can also refer to them as our degrees of freedom, and we have two distinct degrees of freedom, V1 and V2. So, as long as we can fit all of that criteria, we know that we're working with the F distribution. If we want to compare the variance of one distribution to the variance of another, this will be the F distribution. So look out for that in your questions so you know exactly what distribution you should employ. Okay, so if you wanted to generalize, I've written that down at the bottom for you. And just quickly to point out that this is in the formula book, but as always, and you hear me say this all the time, I would expect for you to be quite confident in this before you walked into the exam hall. You would know what you were doing. The F distribution is named after Sir Ronald Fisher, quite a famous British mathematician and statistician. He's done a lot to contribute to the world of statistics, and that's not actually his only expertise, but he's also very well versed and recognized for his works in eugenics and biogenetics. He's made massive contributions to statistics. The F test, or the F distribution, is actually named after him. Incidentally, he is a UCL alumni, so really representing London on the statistics front. So not only do you have a formula available in the formula book, but there's also some tables that are available as well. So these we'll call the F distribution tables. These are critical values linked to the F distribution. And if you have a look, there are two specific probabilities. Let's look at the 5% probability tables. Now, all of these values here will be a critical value that is exceeded only by 5%. We can look these up by using the two parameters for the F distribution, which are V1 and V2. You would have found these by doing nx minus 1 and ny minus 1. So I just want to quickly draw your attention to some features of a graph that we might be able to use for the F distribution. Now typically we're going to have some positive skew, so the graph is going to skew off in the positive direction. And what we have here is a value of 1, because this would be the case if the sample variance for one sample actually equaled the sample variance for the other. Then the division that we're doing, the ratio that we're finding, would be a 1-to-1 ratio. We'll get an answer of 1 for that division. Now, we have numbers that are smaller than 1 and numbers that are greater than 1. We won't have any negative values because that division of one variance and another variance will never give you a negative value. And we can actually skew quite far off towards the right, because a large variance divided by a small variance might give us a number like 10, 15, 28, whereas a small divided by a large is only going to give us a fraction in between 1 and 0. So this is what generates the positive skew when we look at a graph depicting the F distribution. So here we should be able to find these critical values in the tables immediately. It's been stated that V1 is 5, V2 is 8, and we're working at the 5% level. Okay, the order here is important. We'll get a different result if we'd switched around and made 8 V1 and 5 V2. So I'm going to look down the column with the 5, and I'll look across the row with the 8, and we can see here, cross-referencing, we get 3.69. So that'll be our critical value. What if the degrees of freedom were the other way around? Well, we'll look in the column for 8 and the row for 5, and we see this time round we get a critical value of 4.82. So the order is actually really important for V1 and V2 as we're looking them up in the tables. It is going to get to a point where you are going to be the one who's going to identify V1 and V2 from the distributions that you're working with. So be really careful that you're consistent with your labeling or numbering and you're using the right degrees of freedom in the right place. So let's just look at a couple of techniques we can use when looking up values in the tables. Firstly, some values or questions we might be asked to respond to, there may not be something in the table to help. But this equivalence, this statement here, can be useful. So, the F distribution, where you have 2 degrees of freedom for a specific probability, is going to equal the reciprocal with the degrees of freedom swapped and a complementary probability. So the way that I see this is that there's lots of things that are being reversed. First, the order of degrees of freedom have been reversed. Secondly, we found the reciprocal, which is another reversing, and then we found the complement of the probability. Okay, when would this be useful? This is useful when that specific arrangement of degrees of freedom isn't available in the tables. If you have a look at the tables, not everything that is described for V1 is described for V2, and vice versa. So some values are only found in V2. Rather than in V1. It's also useful when the probability value that you're looking for is not in the tables. We only have tables for 1% and 5%. So if we were looking or working with 99%, it might be useful to use this identity to switch from working with 99% to working with 1%, to go from working with 95% to working with 5%. So as long as you're comfortable with this interchange, you should be able to solve any and all problems that are given to you in your practice exercises or in an assessment. And that extends to this probability statement as well, where once again I want you to see that we're doing 3 reversals. We're reversing the degrees of freedom, we're reversing the inequality sign, and then we're reversing the value x to be the reciprocal 1 over x. Okay, so for me, I always just thought to do those 3 reversals and I would have an equivalent probability statement that'll probably be easier to calculate and work with. Okay, so let's actually see this in action. Well, we'll ask for the upper critical value for an F distribution with 8 and 10 as V1 and V2, and we're working with 95%. Well, there is no table for 95%, so immediately I'm going to try and use the reciprocal expression instead. So this, I should be able to find an answer if I do 1 over F with the degrees of freedom swapped. So that'll be F10, 8, and the complement of this probability, so a probability of 5%. So I've done my 3 reversals. This I can find in the tables. I'm going to get 1 over 3.35. And the answer for that is 0.2985. So this time round, the degrees of freedom are 10 and 8 for V1 and V2. But once again, it's the 95% that we're working with. So let's go back for the reciprocal, which will give us 1 over F 8 and 10. 8 for V1, 10 for V2. And we're working at the 5% level. So that gives me 1 over 3.07, which gives 0.3257. Okay, so if a probability is not either 1% or 5%, we're going to look to do this reciprocal equivalence. Okay, so let's just look at a different type of question, and you're going to see how this slots in and is really important when you're completing a hypothesis test on the comparison of 2 different variances. We're going to try and find both the upper and lower critical values. So let's start working at 5%, and the distribution that we've been given firstly is when V1 is 6 and V2 is 10. So I'm going to get this onto a diagram. I can just draw this by hand. Here's my positive skew, and I know that 1 is going to be roughly here. Okay, the upper critical value is a value that has 5% exceeding it. Remember, these tables are all about values or critical values that have a specific percentage exceeding them. So I can quickly find this. By reading up in the tables, I get 3.22. So that upper limit, that upper critical value is 3.22. Okay, what about down here at the bottom? Well, I want a value that is exceeded by 95%. There's 5% below, 95% above. We've seen how to do this now. We need to use that reciprocal expression, that reciprocal equivalent statement. So F610 0.95 equals 1 over F106 0.05. And now this expression in the denominator we can find from the tables. We read up and we get 4.06. Now 1 divided by 4.06 gives us 0.2463. Now that would be the lower critical value. And just looking, does this make sense? It needed to be a number smaller than 1, and yes it is. The upper limit needed to be above 1, and yes it is. So quite a simple sense check there, but obviously if we'd got a value larger than 1 for the lower limit, we would know instantly that something's wrong. So even just a little detail of knowing where 1 should be placed, knowing that 1 would never be in the critical region, that's enough to make sure you're on the right track with your calculations. Okay, let's have a look at this second example now. So this time around, the degrees of freedom are 12 and 8. So let's get to it with the upper critical value. So this is the value that is only exceeded by 5%. Should be quite easy to read in the tables, as long as 12 and 8 are in the right place for V1 and V2. And yes, 12 is in. There is a column for 12 and there is a row for 8. So looking it up, we get 3.28. Okay, the lower critical value, something similar. I need a value exceeded by 95%. I realise that's going to be this reciprocal statement. I get 1 over F8 12 0.05, which is 1 over 2.85, which leaves us with 0.3509. So definitely practice this and lay it out in exactly the same way that I have, so that you're really clear on what you need to do. And as I said, this is going to play straight into a hypothesis test. You getting this cracked right now, you getting this locked right now, is going to help you to conduct a smooth hypothesis test when it comes around. Now, depending on the calculator that you're using, there may well be some F-test critical values built in. And even if that is available to use, I'll definitely recommend that you're comfortable and familiar with the manipulation that we're doing. An assessment question could very easily be assessing that you know the steps that you would need to take to solve or find a critical value. So just in the same way, I would expect you to know the probability function for a binomial distribution or the probability function for a Poisson distribution, even though we know that there is a calculator function readily available to use, we must know the manual technique as well. Okay, there could easily be a reasoning question or a find the mistake question that needs you to be very familiar with this technique. So I don't mind if you have both techniques, but if you only have one, it should be this one. Well, with that said, let's have a look at a question where the calculator really won't be able to help you find an answer. We've been asked to find the probability that x is in between 1 over 5.81 and 5.06. Now, this is in the case where x follows an F distribution with degrees of freedom 8 and 10. Okay, so as soon as we've got this, I want to have a diagram that's really representing what's happening in this question. As usual, I know where to place 1, which means that 1 over 5.81 must be over here to the left. I want to know what percentage is in this shaded area. What percentage is less than 1 over 5.81? Similarly, I want to know what percentage is above 5.06. If I know those two values, I can quite easily tell what's going on in between. Okay, so let's start with the area above 5.06. Well, x follows an F distribution, so I'll just rewrite this as the probability that F810 is greater than 5.06. And just looking through my tables, I'm really scanning, looking to find this value, 5.06. And I find it in the 1% table. So the probability above 5.06 is going to be 1%. Okay, I'll mark that off on the diagram. Let's do a similar thing at the bottom. The probability that x is less than 1 over 5.81. X follows an F distribution with 8 and 10. And I can already see I've got a reciprocal. I already know that the F tables only really work for the values that exceed a probability that exceeds a specific value. So a couple of clues that I need to use that reciprocal identity. So I can rewrite this as the probability that F108 is greater than 5.81. I've done my 3 reversals and I'm looking for 5.81 in the column for 10 and the row for 8. And I don't see it in the 5% table, but I do see it in the 1% table. So I can write this region off as 1%. Well, if I know that those two tails are 1% each, let's revisit the question. The probability that it's in between these two marked values. If those are each 1%, I know that this area must be 98%, and that's the answer to the question we were asked. So, some good use of the techniques that I've covered so far to solve this question. Spotting when I could use that reciprocal identity, and actually just using a good diagram to represent the probability regions that I'd found up to that point. Okay, and let's just see this one more time, this time specifically at the lower tail. So, Find the probability that x is less than 0.25 when we know that x follows an F distribution with 6 and 12 as the critical values. I'm going to start with the diagram. The very first thing, I'm going to mark off this lower tail, since I know I was finding the probability it was less than, and also that number 0.25 was smaller than 1. So I knew where to mark off on the diagram. I know that I can't really use the F tables for less than probabilities. It needs to be a probability that a specific value is exceeded. So we're going to use that reciprocal identity to change some things. We change the order of the degrees of freedom, we change the inequality sign, and we find a reciprocal for the value that we're working with. So from all of this, I get the probability that F12.6 is greater than 4, which is quite a nice whole number to work with. Looking up in the tables, we realize that that belongs to the table section for 5%. So this region right here must be 5%. Okay, so look, as I've mentioned before, this is going to be exactly how we find critical values when we're working with hypothesis tests. And for a robust understanding of how we work with the F distribution, I want you to make sure you're using this manual technique. If you want to use a calculator technique as a way to check, not a problem, but you definitely want to make sure that you can show all of your working out by going through the techniques I've discussed here. Okay, get yourself some practice and we'll move on to hypothesis testing next.